as you know, the theory and the lab are supposed to be helping each other, and that is happening. The lab assignments are actually based on what is covered in the theory class. Okay, for example, A star was covered in the class, and you had to implement this and see it's working along with properties in the lab. So this is a very useful exercise to do. I've seen that what doesn't get clear in the class gets cleared in the lab. So take the lab very seriously and implement what is told to you. So this week's lab will be on Perceptron, okay, and the next week's lab will be on backpropagation algorithm. So those are the topics. So AO star you can implement on the side. We'll see it later. Okay, AO star is not to be demonstrated right now. So we are in sync with the theory class. Perceptron backpropagation, so neural network based algorithms will be seen in this week's lab and the next lab. Okay, and please stop talking. Please stop talking. Please stop talking. Okay, so this is what is to be done, and please remember this lab and theory will be helping each other. Okay, that is the main point. Now, one thing I have seen, because I have been going around in SL1, 2, and 3, talking to various groups, I'm finding that you have to give little more emphasis. In fact, a lot more emphasis on the basics. So when I ask you what is an admissible heuristic, okay, some of you are saying that an admissible heuristic is one which satisfies monotone restriction. But monotone restriction is a subsequent concept. Admissible heuristic is much more earlier and much more fundamental. Okay. Then some of you have said that admissible heuristic is one which leads to optimal path and termination. That is also not the definition of admissible heuristic. Okay. So you have to be mindful of the fundamentals. The admissible heuristic has only one definition. The heuristic chosen for the search space is less than or equal to the actual cost of reaching the goal, the actual cost of the optimal path in reaching the goal from any node. So H less than or equal to H star is the basic definition. Monotone restriction relates to it. Admissibility, that is termination, and optimality, they are consequence of this heuristic. Okay, so please be precise and rigorous. That is the purpose of being in a course. Okay, so please pay attention to the theory and then implement in the lab. Okay, don't take this sloppily and casually. The definitions are very important. Terminology is also very important. So I have been going around in the lab, and it is quite revealing for me to see some of you are excellent in picking the right concept as taught in the class. Some of you are not so careful, so that should not be. Okay, so now let's proceed. Today we would like to do the perceptron capacity in more detail and also start feedforward neural network if possible. Now, main points covered in the last week, the week 3 of 20th January 25, are the following. We covered the concept of monotonicity, which is a very reasonable restriction on the heuristic. It is triangular inequality. The cost of going from the parent to the goal is less than or equal to cost of going from the parent to the child, that is cost P comma PC, plus the cost of going from the child to the goal node. So it's a triangular inequality. And monotonicity has very nice consequences. One is any heuristic that satisfies monotonicity is also admissible, though the reverse is not true. And this is an important property. The other property is that if monotonicity is satisfied, then any node you pick up for expansion must have got the optimal path to it from the start node. So for that node which has gone to the closed list, the parent pointer redirection is not necessary, which is a lot of saving on the computation and the programming effort. Okay, which also you probably have seen in the lab. And the other point is that if monotonicity is satisfied, then the F values of the nodes expanded from the open list are non-decreasing. Okay, so the FL either remains same or goes on increasing. So these three properties are very nice properties, all of which can be proved, and the proofs are given in the slides. Okay, so this is monotonicity. We covered it in detail. Then this is the theorem which says that any node picked up for expansion has already found the optimal path from the start node to that node. Monotonicity, admissibility, we have discussed already. Then we looked at some of the fundamental points about neurobiology, neurophysiology, neurobiology. The fact that brain has these three components: higher brain, cerebellum, and cerebrum, and these have their own functionalities. Okay, cerebellum is for routing information. Higher brain is for things which make us human beings. Okay, music, mathematics, fine arts, literature, science, and so on. And cerebrum is the vital component, vital part of the brain, which regulates blood flow, breathing, and so on. Okay. Now, Maslow's hierarchy, we have where we noted quite interestingly has this software-hardware correspondence. Okay, that Maslow's hierarchy is a pyramid structure, where at the base of the pyramid is survival, which corresponds to the cerebrum, the lower brain, very well protected from everything. And at the highest level of the pyramid, which is very lonely, I should say, is the set of people who contribute to humanity. And that surely corresponds to the higher brain functions. So we also know about the left brain, right brain dichotomy. For right-handed people, the left brain deals with logic, reasoning, verbal ability. Right brain deals with emotion, creativity. Right brain is also intuitive and holistic. It has it likes the whole picture, not details, but a complete picture of the situation. Then we move to perceptron model. The perceptron actually is a computing device which takes the dot product of the weight vector and the input vector and compares with threshold, and then fires or doesn't fire. Perceptron training algorithm is a very simple algorithm where we take the pre-processed vector, start with an initial weight, and keep on adding the vectors which failed the test of w dot xi greater than 0. If such a w has been found, which satisfies w dot xi greater than 0 for all vectors, then this is the required weight, and the perceptron has been trained. This is the algorithm we will have to implement in the class, okay, and see its behavior for different problems. Then perceptron training algorithm for large problems will take a very large number of steps. Okay, and one of you asked a very interesting question: is perceptron algorithm training algorithm the best algorithm? Okay, for training the linearly separable classes. So this answer I'm looking for. Probably you are also looking for. It's an excellent question. Now, perceptron training algorithm has to converge, whatever time it takes. It may take millions of years, but it has to converge if the vectors are from a linearly separable function. Okay, so if the vector, for example, has, let's say, 10,000, 20,000 components, which is not uncommon for very complex problems like weather prediction, okay, agricultural yield, mental health monitoring. Does a person have depression or not? Okay, so those kind of problems have very large input size. The vector, it has enormous number of components. So even for 1,000 components, the perceptron training algorithm might take enormous amount of time, but it is guaranteed to converge, which we have proved by using the function GWN and examining its properties. So these were the main points covered in the last week. If you have any comment or question, you're welcome to make it. No? Okay. So let's now move to the topics for content for today and this week. Perceptrons and their computing power. So we have this fundamental observation that the number of threshold functions computable by a perceptron is equal to the number of regions produced by 2 to the power n hyperplanes obtained by plugging in the values of x1, x2, x3 up to xn in the equation. This is a defining equation. Sigma wixi equal to theta. Okay. So you take this equation or the equation of the hyperplane, which separates the 0 class vectors from the 1 class vectors. These vectors are points, okay, in an n-dimensional n plus 1 dimensional n-dimensional space because there are n input components. Okay. Then the geometrical observation is that if there are m linear surfaces which are called hyperplanes, note that each hyperplane is of dimension d minus 1. Okay. So these hyperplanes are in d dimension. Then what is the maximum number of regions produced by their intersection? This expression is important for us because we have this fundamental observation that the computing power corresponds to the number of regions produced by 2 to the power hyperplanes, 2 to the power n hyperplanes in the d-dimensional space. Okay. So what is RMD? Okay, so we got an intuition of how to do it. We saw that the regions produced by lines, not necessarily passing through the origin. So when L1 comes in, it produces 2 regions. When L2 comes in, additional 2 regions are produced. Why additional 2 regions are produced? There is a way of thinking about it. Okay, and if we do not think that way, then the problem becomes very complex. The thinking is that the existing line is cut into 2 regions by the new line. Okay, so the number of new regions produced is the number of segments produced on the incoming line by the existing lines. Okay, so this is a different way of thinking about the problem. So that is the main point. So when L2 comes in, the number of regions produced is 2 plus 2 equal to 4. When L3 comes in, then that is intersected into 3 segments, right? Into 3 segments by the existing 2 lines. And therefore, it adds 3 more regions. Okay, so this is the way to think about it. It's a very useful way of thinking. So we'll exploit this in the upcoming slides. So see how it gets developed. 2 plus 2, 2 plus 2 plus 3, 2 plus 2 plus 3, 4, and so on. Okay. You can also set up the recurrence relation for this. So the number of computable functions by a neuron are obtained from the defining equation of the hyperplane. Okay. So let's move to the derivation of the number of regions produced by the hyperplanes. So number of regions found by n hyperplanes in d-dimensional space passing through the origin is given by the following recurrence relation. Rn comma d is equal to Rn minus 1 comma d plus Rn minus 1 comma d minus 1. So Rnd is the number of regions produced by n hyperplanes in d dimension, which must be equal to number of regions produced by existing n minus hyperplanes in d dimensions plus additional regions produced by the incoming hyperplane. Now the incoming hyperplane is of dimension d minus 1. And that is intersected by existing n minus 1 hyperplanes. Okay, so the expression for these must be Rn minus 1 comma d minus 1. Okay, so this is the recurrence relation. So the recurrence relation must be clear to you from the example of working it out for lines, planes in 3-dimensional space, and so on. The boundary condition is this: R1 comma d is equal to 2. So that's intuitive. In the d-dimensional space, only one hyperplane produces 2 regions. And Rn comma 1, in the 1-dimensional space, which is a line, the number of regions produced by n hyperplanes, which actually happen to be dots. Okay, and all of them pass through origin. So that also produces 2 regions. Okay, so the boundary conditions are clear. Now we have to make use of this recurrence relation to find out the expression for Rn comma D. That is our final goal. So this is typically solved by generating functions. Let's see what generating function we can use. So since there are two parameters, n and d, we set up the generating function this way. Now the generating function is called so because it generates the entities in the recurrence relation through their coefficients. Okay, the expression for the entities in the recurrence relation through their coefficients. So fxy is equal to Rnd, this is of interest to us, into x to the power n into y to the power d. N goes from 1 to infinity, d goes from 1 to infinity. This is our generating function. Okay. From this, we will perform mathematical operations to obtain the value of Rn comma d. Now, from the recurrence relation, we have this equality Rn comma d minus Rn minus 1 comma d minus Rn minus 1 comma d minus 1 equal to 0. Okay. Rn minus 1 comma d corresponds to shifting n by one place. Okay. So if we multiply the generating function by x, then we'll achieve this effect of shifting n by one place. And our n minus 1, d minus 1 corresponds to shifting n and d by one place, multiplication by xy. So let us see how it happens. fxy is r11 xy, r12 xy square, r13 xy cube, and so on up to infinity. Then change n equal to 2 now. R21 x square y, R22 x square y square, R23 x square y cube, R2d x square yd up to infinity. And then finally Rn1 x to the power ny, Rn comma 2 x to the power ny square, and so on up to infinity. Okay, this is the expanded form of fxy. Now fxy is this. If we multiply fxy by x, then what we get is x fxy is equal to n equal to 1 to infinity, d equal to 1 to infinity, r and d x to the power n plus 1 y to the power d, which is equal to n equal to 2 to infinity, d equal to 1 to infinity, r n minus 1 comma d x to the power n y to the power d. Okay, so we have been able to achieve this goal of getting the coefficients r n minus 1 comma d. Okay, and if we multiply fxy by xy, then we get n equal to 1 to infinity, d equal to 1 to infinity, r n comma d x to the power n plus 1, y to the power d n plus 1. And that can be written as n equal to 2 to infinity, d equal to 2 to infinity, r n minus 1 comma d minus 1 x to the power n, y to the power d. Okay, so we are able to get r n minus 1, d minus 1 also. So fxy now can be written as n equal to 2 to infinity, d equal to 2 to infinity, r n minus 1 comma d x to the power n, y to the power d, plus n equal to 2 to infinity, r n minus 1 comma 1 x to the power n y. Okay, and that will be equal to n equal to 2 to infinity, d equal to 2 to infinity, r n minus 1 comma d x to the power n, y to the power d, plus 2 into n equal to 2 to infinity x to the power n y, 2 because of the boundary condition. R n minus 1 comma d is equal to 2. Okay, so we have come up to this step. Then fxy is again this expression, which can be written as n equal to 2 to infinity, d equal to 2 to infinity, r n comma d x to the power n, y to the power d, plus d equal to 1 to infinity, r 1 comma d x y to the power d. And then plus n equal to 1 to infinity, r n comma 1 x to the power n y. Now R11 xy gets counted twice, considered twice. So we subtract 1 R11 xy to preserve the equality. Okay. And then we have n equal to 2 to infinity, d equal to 2 to infinity, Rn comma d, x to the power n, y to the power d. Apply the boundary condition. R1 comma d is 2. So this becomes 2x d equal to 1 to infinity, x y to the power d. Again, apply boundary condition. 2y n equal to 1 to infinity, x to the power n y minus 2xy. R11 is again the boundary condition. Okay, so we have got xy, fxy in this form. So after all this expansion, if we take the subtraction of the left-hand sides, then fxy minus x fxy minus xy fxy gives me n equal to 2 to infinity, d equal to 2 to infinity, Rn comma d minus Rn minus 1 comma d minus Rn minus 1 comma d minus 1, x to the power n, y to the power d. Plus 2y into n to the power infinity xd minus 2xy minus 2y into n equal to 2 to infinity x plus 2x d equal to 1 to infinity y to the power d. And that is equal to the 2x into d equal to 1 to infinity y to the power d through cancellations. Okay, through cancellations. So since other two terms become 0. Now, this implies, now you see this is also equal to 0 because of the recurrence relation. So what this implies is that 1 minus x minus xy into fxy is equal to 2x into d equal to 1 to infinity y to the power d. So fxy is equal to 1 by 1 minus x into 1 plus y, 2x into d equal to 1 to infinity y to the power d, which can now be expanded 2x into y square, y cube, y to the power d up to infinity multiplied by, this is the expansion of the form 1 by 1 minus x, which is 1 plus x into 1 plus y plus x square into 1 plus y square, and so on. Okay. Also, we have fxy is equal to n equal to 1 to infinity, d equal to 1 to infinity, r and d, x to the power n, y to the power d. Okay. So comparing coefficients of each term in the RHS, what we get is this, you should do yourself. Okay. R and d is equal to 2 into I equal to 0 to d minus 1, ci n minus 1. Okay. So the expression for R and d, which is the number of regions produced by n hyperplanes in d dimensions, is equal to 2 into I equal to 0 to d minus 1, n minus 1 choose I. Okay. So this you should verify by comparing coefficients. Now, what is the implication of this? For a perceptron with m weights and 1 threshold, R and D becomes R 2 to the power m, comma m plus 1. Okay. So to the power m hyperplanes passing through origin, and the dimension being m plus 1. Why m plus 1? M weights and 1 threshold. Okay. And why 2 to the power m? Because x's can take 2 to the power m values. And this would be equal to 2 into I equal to 0 to m plus 1 minus 1. 2 to the power m minus 1 choose I. So this is equal to 2 into I equal to 0 to m c to the power 2 to the power m minus 1 choose I. And this can be shown to be equal to order of 2m square. Okay. So the total number of Boolean functions is 2 to the power m, whereas total number of threshold functions is 2 to the power m square. So there is no way threshold functions can catch up with Boolean functions. The number of threshold functions can catch up with Boolean functions. Impossible. Okay, there is an order of magnitude difference, 2 to the power m square versus 2 to the power 2 to the power m. This explains why the number of threshold functions fall so drastically. For 64,000 Boolean functions. The number of threshold functions is only 1008. Okay, for 256, 128. So it decreases very fast as the number of inputs increase for the perceptron. So this means that perceptrons have very limited computing power. That's true. Okay, and therefore we have to do something about it, which we are going to do. Okay, now what I very strongly suggest is that you go through these derivations and try to derive these expressions yourselves. Two expressions. One is this comparison of coefficients, and the other is this order 2m square. The processing of recurrence relations to generating function are systematically presented step by step. Okay. Any question, comment? Okay. Okay. So perceptron training algorithms convergence we have seen. I just want to re-emphasize the specific points. In the proof, the most important step is the first step. Thinking of GWN, which is wn.w star by mod of wn, which doesn't seem to be extremely out of the way. Okay, it is a measure of distance between the current hyperplane and the required hyperplane, which does the job of separating the positive points from the negative points. And this way of measuring the distance between two vectors and hyperplanes is our bread and butter in deep learning systems. Okay, when we work with deep learning to solve any problem, could be scene understanding, could be robotics, could be language understanding, anything. The distance between two vectors in terms of their cosine similarity is fundamental. Okay, you will see it in future when you go through deep learning based AI systems. So this is, so you can see the genesis where all this started. And this distance, we do not want to influence by the size of the vector. So that's why there is a normalizing influence by taking the mod of wn, dividing that cosine distance or the dot product of wn w star by that scalar. Now GWN we see is expanded as mod wn dot mod w star into cos theta, where theta is the angle between the two hyperplanes. So divided by wn, mod wn cancel. So we get GWN is equal to w star cos theta. W star has to exist because the vectors are from a linearly separable function. Okay, so we are not we do not know that w star, but it has to exist. So GWN then is upper bounded by the mod of w star. So then we investigate the property of GWN. So wn.w star is the numerator. Wn came because wn minus 1 failed for some vector. And the perceptron training algorithm asks you to add the failed vector to the current vector. So wn minus 1 plus x to the power n minus 1 fail. So this is the failed vector at the n minus 1th iteration of the algorithm, multiplied by w star. So note that this w star dot x fail has to be greater than 0 because w star separates the positive class from the negative class. So if that happens, then we move backward from wn minus 1, we move backward to wn minus 2, and so on. So finally, we have this expression w0 dot w star. W0 is the initialized vector multiplied by these w star dot all the failed vectors. So w star dot all the failed vectors are some positive quantity. This is appearing n times. So the numerator grows as n, linearly with n. How about the denominator? Denominator is square root of wn dot wn. Okay, so all these this whole square root is extending over the whole expression. It's not only on Wn. So Wn minus 1 plus fail vector square is the expression coming from this, which is Wn minus 1 square plus 2 into Wn minus 1 into x fail plus x fail square, and the square root extending over the whole expression. Now this must be negative or non-positive. Okay? This must be less than or equal to 0. Therefore, this square root expression of Wn minus 1 square plus x fail square must be less than or equal to 0. So if we move backward, then towards w0, then we find that this square root expression extends over an expression which has w0 square plus the squares of all the failed vectors. Now the squares of each failed vector has some definite magnitude. And if there is some maximum magnitude rho, then the denominator increases as square root of n, because these failed vectors appear n times. So denominator increases as square root of n, numerator increases as linear in n. Therefore, GWN has to become infinity as n tends to infinity. But GWN is upper bounded by W star, mod of W star. It cannot become infinity, which means n cannot become infinity, where n is the number of iterations. So if n cannot become infinity, that means the algorithm has to converge. Okay, so this is a very elegant proof and one of the most beautiful proofs in AI. So this you must have noted. Okay, so this gives us a lot of confidence that perceptron training algorithm will have to converge. Okay, so now let's begin arguably the most important topic of deep learning. Okay, a piece of work which got one of the authors of backpropagation, one of the three in the physics Nobel Prize, the Nobel Prize itself. Okay, it is backpropagation. So the whole of neural network-based AI, connectionist AI, is founded on backpropagation. So we would like to understand backpropagation, though the algorithm is very empirical. Very little is known about the theoretical properties of backpropagation in the general case. And backpropagation is used in so many large applications and so many diverse applications. Metallurgists use them to predict properties of materials. Economists use them to predict, let's say, the stock market movement. Physicists use them, chemists use them, protein structure prediction, and so on. Everywhere it is backpropagation at work. And this algorithm you will have to implement in the class and see it's working on problems which are not solved by a single perceptron. Okay, so backpropagation makes use of what is called multi-layer perceptron. So the name should be obvious. It is an assembly of perceptrons which are all put together, connected with each other. So feedforward network and backpropagation. Let's understand the feedforward network. Now we know that XOR cannot be computed by one single perceptron. When you set up the linear inequalities, you find that it is an inconsistent system of inequalities. When you run perceptron training algorithm on XOR, you should notice interesting things, which I'm not telling you now. But you should observe the behavior of the perceptron training algorithm on XOR. So XOR cannot be computed by a single perceptron, but it turns out that it can be computed by more than one perceptron put together. So what is the architecture? Architecture is this. It is the final neuron in the uppermost layer, which becomes 1 or 0. Okay, 1 or 0, based on the inputs. So if the inputs are 0, 0, the output has to be 1, 0. If the inputs are different, 0, 1, 1, 0, output has to be 1. If the inputs are same, output is to be 0. Can this be computed? Yes, it can be. If we note that XOR is actually a composition of linearly separable functions. XOR is x1 bar x2 plus x1 x2 bar, where plus means the OR function. Okay, so you can compute x1 bar x2 by a single perceptron. You can compute x1 x2 bar also by a single perceptron, and you can compute OR definitely by a single perceptron. Okay, so all these functions x1 x2 bar, x1 bar x2, and OR, all these can be computed by a single perceptrons. So this architecture is absolutely fine for computing XOR. Okay, you are convinced? Okay. You can also compute XOR through the AND function. So this can be the AND function, which is computable by a single perceptron. And this neuron computes x1 plus x2, OR. And this neuron computes x1 bar plus x2 bar. That is NAND of x1 and x2. Okay. So one neuron computes NAND of x1, x2, which is linearly separable. Another computes OR of x1, x2, linearly separable. And the final neuron computes AND. This is the other way of doing XOR. Okay. So OR of two constituent functions or AND of two constituent functions. Now, what is the pitfall here? What would you say are the criticisms? I mean, everything looks very nice, very fine. What are the caveats? XOR is fine. So this looks for compositionality. Okay. A function which is not computable by perceptron is decomposed into a set of perceptron computable functions and their composition, again by a perceptron computable function. So imagine mental health prediction. Okay, from the social media posts of a person or emails or utterances or the picture of the person, conversation with somebody, you want to predict if the person has any depression or not. Enormously complex problems. So you can imagine that there will be an input vector of, let's say, size some, let's say 80, 90, or even 40. And the output is again a 1-0 decision. Has depression, doesn't have depression. Now, the first question to ask is it a linearly separable function? So given the various parameters of the individual, can we predict depression or not? So is it a linearly separable function? It turns out that most problems in real life are not linearly separable. How do you know? There is no proof. You just take one perceptron and keep running. After an enormous amount of time, there is no decision, no convergence. Okay, so it's a tricky situation. We do not know if the function is linearly separable. It may be linearly separable, but I cannot wait. That is the problem. Okay, so I cannot wait indefinitely. After 1,000 years, the answer will come, maybe, but who will be alive for 1,000 years? Okay, so you'll have to make use of some engineering decision, which is that after a reasonable amount of time, I'll stop it. And then do what? I assume that these weights are fine. Okay, of course, this architecture is not exactly this. There are very large number of neurons in the input. We do not also know how many layers are there in the intermediate stages and how many neurons are there in the intermediate layers. So this is the intrigue of feedforward network. By the way, these networks are called feedforward because the information flows from input to the output through these layers, and there is no backward flow of information. It's feedforward. And at every layer, if every neuron is connected to all neurons in the previous layer only, then it is called a complete feedforward network. And if there is no jumping of connection, each neuron is connected to only the neurons in the previous layer. It is called a pure feedforward network. Feedforward network, complete feedforward network, pure feedforward network. These are the terminology. I do not want you to be shaky on any of these definitions. Okay, in the lab, I'll ask you, what is a pure feedforward network? You should say that there is no jumping of connection. Why is it called feedforward network? There is no backward flow of information. Okay, there is no backward actual signal flowing. And why is it complete? In any layer, every neuron is connected to all neurons in the previous layer. Okay. Now this is this an architecture. So feedforward network is an engineering exercise. Okay, you'll have to do a lot of trial and error with the number of layers and the number of neurons in per layer. So I want you to get that experience. You will be given some data sets. Okay, and you will have to implement backpropagation and train a network on those data sets. Okay, so let's complete the story of this depression detection. So we stop the feedforward network from training after a while. When do I stop? I say that if the error which is shown here, the difference from the target behavior, if the error falls below a particular value, then I'll stop the network. Okay. So how do I know the error? You are given what is called the validation data, test data, validation data. Okay, for which the labels are known. So you are given, after training, you are given a set of data instances where the person has depression, the person doesn't have depression, all those label data is given. And then you check the label of the trained network against the reference values. And from that compute the error. How do you compute the error? The error is typically computed by two methods, what is called cross entropy and total sum square loss. We'll look at all these losses going forward. And then this is acceptable to you. This is fine. Now comes actual unseen examples. Here is a new case of a person with all the input data. And you find that person after person, there is false positive and false negative. A person not having depression is labeled as having depression. A person with depression is falsely labeled as not having depression. These are false negative and false positive cases. And there are so many of them, you know that this training has been completely useless. So what you have to do is that you have to retrain the system with changed architecture. Architecture means more layers, more neurons maybe or less neurons. So you have to play with this architecture. So you should get that experience in the lab of taking a piece of data and getting quite frustrated because the training error is not reducing or the performance on the unseen data is abysmal. You should have all those experiences. Okay, so some fix the optimum number of layers and the number of neurons per layer. Okay. So for XOR, we see that the correct weights are the following. From x2 minus 1 to the first hidden layer neuron, let's call this H2. And from x1, the weight is 1.5 and the threshold is 1. This neuron will achieve x1, x2 bar. And the two weights up to the other hidden layer neuron. These neurons, by the way, are called hidden layer. They do not interact with the environment. They do not receive inputs. They do not give out outputs to the environment. So -1, 1.5. So this achieves x1 bar, x2. And OR we have already seen how OR can be computed. The two weight values are 1, 1, and the threshold is 0.5. This computes OR. Okay, so this is very nice. And this network is computing XOR. Similarly, XNOR can be computed. But for real life actual problems, this way of decomposing the function is impossible. First of all, you do not know the nature of the function. Okay, for weather prediction, what is the nature of the function? For depression prediction, what is the nature of the function? Loan application scrutiny, what is the nature of the function? We don't know. These are mappings, but the functions are not known. Okay, so this is a very ideal case, but very good for conceptualization. Now, we apply what is called the gradient descent technique to minimize the error. The error is a function of the weights of the connections. So I have shown here an example, one kind of error, which is called. So if Ti is the target output and OI is the observed output, then Ti minus OI whole square is a quantity contributing to error. So I is the index going over n neurons in the outermost layer. J is the index going over the P patterns, 1 to P. So if it is XOR, then J goes from 1 to 4, 0, 0, 0, 1, 1, 0, 1, 1. And how many neurons in the outermost layer? Only 1. But there could be cases where you have more than 1 neuron in the outermost layer for problems which are of mapping kind. Okay. For example, this network with more neurons in the outermost layer can be used for digit recognition. Okay, 0, 1, 2, 3 up to 9. So I give the unary representation or binary representation of these digits. And in the outermost layer, I have the detection. Okay, so yeah, let's say the outermost layer is unary representation and the input layer is binary representation. So if the digit input is 9, then the 9th neuron counting from 0 becomes on. But what is actually done is a set of pixel is given for digit recognition, a set of pixels. Okay, so you know the 8-segment display. In 8-segment display, there are 8 segments which can be lighted up or kept dark to represent any digit. So those 8-segment displays, their on and off state is input in the input layer. There are 8 neurons. And then you get the output as the required digit. Okay. So, the total sum square error is computed over the square of the difference between target and observed, running over all the neurons in the outermost layer and running over all the patterns in the data set. Okay. And this scheme of things is universal. Take any deep learning problem, neural network based AI problem. This is the structure. Okay. Now, this is called total sum square error. Many times we have to compare probability distributions. Okay. What is the probability that this sentence has positive emotion or negative emotion or neutral emotion? Okay, what is the probability? Or what is the probability that this robot will take left turn, right turn, or move forward or stop? There are 4 possibilities. Each of these has a probability. So we compare the target probability distribution with the observed probability distribution through a loss function called cross entropy loss. At that time, we cannot use total sum square loss. Why? Because probability values are between 0 and 1. So these are small values, and their difference will be still smaller. Their square will be still smaller. So total sum square loss for comparing probability distributions is not at all a good idea. We have to use cross entropy. So all this will be, very systematically done, slowly done, and you will make use of them in the lab in your implementation. Okay. So let me stop here today, and we'll continue this discussion.